Now, how did you do it? You can see how they're going to introduce integration by parts into this. So there was your first step, right? You start from this left-hand side. And the first thing you had to do was identify an appropriate u and dv. Okay, so here's the way that I did it. This is the way I broke it apart. That gives you du. By the way, things like that negative sign, right? That's where you started to have problems. And being that you were required to show something, this happened lots and lots, right? You left off a negative sign, one which was needed to get this result, right? But then, having left that off and then gone through, you're like, oh no, I've gotten to some line which can't get to what I'm trying to prove. So you did some fudge kind of down here. That's got to be a signal to you. You've got to learn to recognize that. When you get down after 5 or 6 lines and you're like, I'm not seeing it, I'm not getting it, I've got a negative when I should have a plus. Don't try and fluff around down here and do a fix. Doesn't work. You've got to go back up. Clearly it tells you you've done something wrong like this. Okay? So that's exam technique for proofs like this. Especially when there are a lot of marks at stake. Okay? Right, so you had x to the m here, which gave you v. Okay, so there you go. There's all our pieces. So let's do this. Will I have enough space? Move it over a little bit. Now, because it was a definite integral, your uv part was actually being evaluated from 0 to 1, right? So this is what you started with. There you go. Okay, so it's really nice and easy over here because when you evaluate 0, this becomes 0, so that's nice. And when you evaluate 1, this becomes 0, which is nice. So that disappears. But what you cannot do, just like with that previous question with the definite integral identity, you can't just make it disappear. You have to say it equals to 0, okay? So, little things. Really, you should have said it's equal to 0 minus 0 because there's 2 things there being evaluated, both of which are 0. You've got a double negative happening here, so that's why this turns into a plus. You can take out all your m and n terms because they're just constants, yes? So this goes from 0 to 1, and then you've got this guy. Okay, now, I think that's what we wanted without the zeros at the front, so that part's done. But when you move into part 2, what were we asked to do? They wanted you to use this part to get to this expression for this recurrence relation for in, right? So how do you do it? How do you get rid of this guy in here, right? Well, you can start off from here. You'd say in equals, and clearly it's going to be in here. Something in here is going to have to interact with each other so you can get that n power, right? So here is where I went. I said, okay, we can say this from the first part. Okay. Now, what can I pull out? Well, I've got an extra x here, don't I? Right? I've got an x to the power of m plus 1. So if I write that in as x to the m times x, that's good, right? Okay, now that guy there, he's the key. He's going to unlock this whole thing, right? We just need to get him in terms of 1 minus x, right? How am I going to do it? Suggestions? Take a seat. What do we make it equal to? Minus.
Oh, but then you can just add it and then minus it.
Yeah, what do I want? I want a 1 minus x out of this, right? I think probably the easiest way is, because I have this 1, first I've got to add that in, right? But if I've added that, I have to subtract it as well, yeah? So if I subtract it, this is what I want to take away, okay? Can you see the 1's going to disappear because it's not really there, right? And those double negatives will cancel, leaving you back with the original x, right? So we looked at an example like this before. In fact, we looked at a tricky one with like 3's and 2's in it and that kind of thing, okay? So I think we should have been able to spot this. Then you've got your 1 minus x to the n minus 1 over here, okay? Can you see what's going to happen? let's have a look. So you've got n over m plus 1. There's your integral. Okay, what do we get? First, you're going to get, I'll do it in this color, x to the m times 1 times 1 minus x to the n minus 1. Okay, that whole piece, right? So this is what you get out of that. X to the m, 1 minus x to the n minus 1. Okay, I haven't split it apart yet. Okay, so there's the first part, and I know what that's equal to in terms of my other integrals, okay? Then I've got this other guy to factor out. I've got x to the m times negative 1 minus x times 1 minus x to the power of n minus 1, right? Okay, so these 1 minus x's will come together, and with index laws, that'll become an n, right? So here's what you end up with. Minus. Let's chuck some big brackets around that. There you go, okay? That was the critical step. Once you saw that, the rest of it kind of falls out from there, right? What happens? You can split this apart into two separate integrals. So you've got an n over m plus 1 here. What is this integral? What is it in terms of the notation that we've already introduced? This is I of n minus 1, isn't it? You see that? Bless you. Okay. Then I'm going to take away. I've still got that n over m plus 1 out the front. But what is this? That's just in. Cool. And now that's the integration done there, right? That's all equal to in. Now what did I want to do? I wanted to make in the subject, that's all, right? So when you add this back over, what are we going to get? Actually, probably if we multiply through, that might make it a bit easier. So you'll have n plus 1 of these guys, n of these guys, and n of these guys. Kick that n over the other side. So it's going to become m plus n plus 1 of those. Are you following? Did you see what I did? And now I just have to divide through, right? Yeah, I've just got enough space. N over. Okay, and there's the recurrence relation. Hooray! That wasn't so bad.